Today we cover one of the premier laws of physics that was developed and formulated by Michael Faraday in the early 1800s. And one can truly say that it was Faraday and this particular law, especially, that sort of ushered in the modern electrical technology that gives everything we know about modern day society at this point. Sort of created modern society. Yeah. To set the background for it, we've to this point been concerned with steady, constant currents, and as we've seen, Ørsted in 1820-21 discovered that a current-carrying wire produces a magnetic field around the wire, and that experiment, and I think everybody recognized that it clearly showed there was an intimate connection between electric fields and magnetic fields, at least in the following sense. Think of it this way: I've got a parallel plate, charge plus Q and minus Q, and we know that creates in between the plates an electric field everywhere. And if I place a wire or maybe a cylinder, a metallic cylinder between the two, then this electric field will cause currents to flow through this. So we essentially have an electric field producing a current flow, and the current flow by Ørsted produces this magnetic field. So that sort of was the logic. The electric field essentially produces a magnetic field. It goes through this intermediate of producing a current, and then the current in turn produces the magnetic field. So with the experiments of Ørsted and Ampere, Biot, and Savart, many researchers turned to look to see if you could do the reverse process. In other words, if an electric field can produce a magnetic field in this sense through some intermediary, what can we do so that, since these two phenomena are so closely related, to have a magnetic field produce an electric field? So they were looking for some process with an electric field to create with a magnetic field to create an electric field, sort of the reverse of this one up here. The typical approach was to just take a wire with no current in it, and then hold a magnet up close to it, and thinking that would produce a current flowing in the wire, which all those experiments failed. But another way of looking at it was developed by Michael Faraday. He actually began looking at it shortly after he learned of Ørsted's discoveries in the 1821, probably. And he looked at this problem for the next 10 years before really finding a solution to it. So it took him a decade. And you have to realize that Michael Faraday was really a genius, particularly in terms of physical insight and experimental technique. He was very famous in his day for a book that he wrote called The Chemistry of Candles. You might imagine 1830s, there isn't any electric lights and there's no gas lights. The only lights you have is either your fireplace or with candles. And so candle production was a big state-of-the-art technology. And anything that could improve a candle's illumination or make it burn longer, make it last longer, was particularly welcome. And Michael Faraday basically looked at the chemistry of candles to try to improve those, and was famous really in his day primarily for that. It's kind of an interesting book. It's the last time I looked, it was still in print. The Chemistry of Candles by Michael Faraday. But if it's not in print now, then you can find it in lots of libraries. So it's kind of interesting to see his take on things and the way he thought and progressed through it. Uh, Faraday was kind of an interesting guy. He was more or less self-taught, and he just did not have much of a background in anything mathematical. So he certainly was not able to do calculus in the normal sense, anyway. And he was, as I probably have told you before, uh, he had great physical insight, however, and he sort of made up for his lack of math ability. He could do algebra and maybe some simple trig, but that was about it. Certainly no calculus. And yet as we'll see, Faraday's law is best described in terms of calculus, and as is a lot of things in physics. And Michael Faraday was sort of handicapped in that regard. Probably not because he wasn't smart enough; he just didn't have the background that it did not have any formal learning in it. But to compensate for that, he developed a great physical insight, and in some regards, it was the motivating factor of why he um, really invented the concept of electric field and magnetic fields, uh, which has revolutionized physics. Everything now is all forces are produce force fields, and the all due to Michael Faraday. Uh, Faraday, uh, even for him, 10 years was a long time. And I don't want to say that he was always working on this particular problem of how to relate how to create an electric field from a magnetic field, but because he certainly did other things. As we've seen, he came up with the concept, the electric field concept. He did the experiments with capacitors and dielectrics, and so all of those were things that he did. He wrote his book on the chemistry of candles, etc. So, but he was always coming back to this problem and thinking about it and trying different things experimentally. Um, you can another thing about Faraday is that he kept meticulous journals. I think they're still published as far as I know, but they may be called Michael Faraday's journals. And but they would be what we would nowadays probably call a laboratory notebook. And so you get a lot of insight into his thinking and the way science was conducted back then by reading through those. And again, I think they're still in print. If they're not, lots of libraries have copies of his journals. So, well, let's take a look at his experiments that sort of revolutionized the world. We wouldn't have electric power transmission the way we do anyway. We wouldn't have AC current running everywhere without these seminal experiments. The first experiment I'll look at is the following. He basically makes a closed circuit over here, which one end he rolls into a loop. This should be I meant to go behind this wire, so that's why it's a little break here, but this is a continuous wire segment, but there's nothing else in it. There's no batteries, no anything, except for a device to measure the current. And today I've taken some liberty in just calling that an ammeter. So remember, an ammeter is a circle with an A in it. In Faraday's time, they didn't have what we would call an ammeter, but they had the beginnings of it, which was called a galvanometer. But it was a current detection device. But like a modern day ammeter, if we were going to recreate his experiment, we'd just use a multimeter and put it in current mode. And but in modern day, or in his day, he used a galvanometer. So sometimes he uses the experiments with a G here to indicate galvanometer, but it's just a current measuring device. In particular, he was focused if there was any current flowing at all, and also what direction. And so the galvanometers could give them, indicate roughly how strong the current was, if there wasn't any current, and also give the direction of the flow depending on which way the needle in it moved, essentially. And he had developed this experiment in which he formed a closed circuit, formed one end in a loop, and then would move a magnet toward it. And what he found is that if you just held the magnet there stationary, you got no current flow. If you pushed it in while it was moving, you got a current flowing in one direction, and if you pulled it out, you got current going in the opposite direction. So this meter would switch directions. Now that sounds like a pretty simple experiment. Nowadays you can go for $10 and buy an ammeter that could measure this and do this experiment. He, however, didn't have the strongest magnets in the world. Certainly not very strong by today's standards. And then his meter he had to build himself. He couldn't go to a Lowe's and buy a current meter. So he had to build all of this stuff, and even making the wire was no mean feat in those days to connect things with. But to give you what he finds is, first of all, if the magnet's not moving, you got nothing. Okay? And now then, we look at this bar magnet, north end, south end. I'm going to have it moving toward moving toward the center of the ring, have it go right down the axis. And when he did that, then what he finds is you got a current going around this ring, essentially going, looking at this picture, they'll be going counterclockwise, going away from us at the top and coming toward us at the bottom when I viewed it edge on. On the other hand, if he did that and then pulled it out, then his meter indicated current going in the opposite direction. So it began to flow not counterclockwise, but clockwise. And clockwise, it would be coming toward us at the top and away from us at the bottom. Again, if it wasn't moving, so if V is 0, it gets nothing. The magnet had to be moving relative to this loop up here. He also found some other things in that if you did multiple turns, so this I've just got a single loop, but if he did n turns, well, he got a much stronger current going through when it was, but still the same effect. If he switched the magnet, however, so that he was moving the south end first toward it, he got opposite current flow directions. And then if he had that same configuration and was pulling it out with a steady velocity, then he got the opposite from the case here. So going in, it produces one direction. Going out produces the current flow in the opposite direction. And then switching the poles also had similar effects of switching directions. So that was one set. So we knew that it had to be something changing with time. When you see this, the things that's happening is changing with time. If it wasn't changing with time and this was just sitting there with velocity 0, then there was no current. So it's something about changing with time is key on it. He did another set that's essentially the electromagnet equivalent of it. He got two of the identical apparatus, except this time on one side of it he puts a battery and has a switch here. When the switch is closed, then this is going to cause the current to flow in the general direction. And then over here, so this is the one with the battery in it. They took to calling the ones with the EMF or the battery that's producing the primary coil in this case, and the one over here with nothing in it other than something to measure the current as the secondary. So you may hear those terms. And in this case, when the switch was open, well, of course, you got nothing. When the switch was closed, he saw that there was a brief instant, and just at the instant this was closed, he got a surge in current over here, but it rapidly went back to zero. And then if there had been a steady current flowing through this after it had been closed for a long time, he got nothing as well. Uh, the, from a side view, this one, the current's going in this direction. On the top, it's coming out at me. On the bottom, it's going away from me. And in the instant that the switch was being closed, what he finds for the direction of it here is the opposite direction to those. But again, it quickly died out. It was really only in this brief instance as the switch was closed that he got any induced current in this secondary coil. The converse of it, if the current had been flowing through this for a long time in that same direction, so it's flowing around up here, and then so the switch has been closed for a long time. There's nothing over here because nothing has changed, and now then, if he would open it up, then the interesting thing was here is that the current, if you look at it, was coming around this direction, so it's coming out at the top, going down. But it's dying out. So these are ultimately going to zero, right, in both of these. And during that instant, that brief instant, as this is opened up and this current begins to die out in the primary, then the current over in this side, you saw the current flow, but it was in the same direction as the current over here had been in. Okay, it's really going from this down to zero, but in that brief instant, it induced a current over here that was in the same direction. And again, it only occurred in that brief instant of just this opening. So it took really very careful observation from Faraday to even notice these effects, especially with the instruments and instrumentation that he had available to him and that he could build. So that's sort of what things went to. And from those, after developing his concepts of the electric and magnetic field lines, so field lines, and also developing the concept of counting field lines, the amount of flux through a surface, he came up with this formulation of what's nowadays called Faraday's law in his honor. And let me just state it first. The EMF induced in the closed circuit is equal in magnitude to the time rate of change of the magnetic flux cutting through the area enclosed by the circuit. So the one he's talking about is this one over here, the secondary. If there's a current flowing in it, then there's an induced current, and we know that currents are produced through wires by EMFs. Now, there's no battery in it, so there's no physical current, no physical EMF like this, but somehow there is an effective EMF that's induced in this to produce that induced current. Again, lots of experiments that went into this. We would probably write it nowadays in the following form, that the magnitude of the induced current is equal to really the magnitude of the time rate of change of the magnetic flux. So that time rate of change is calculus, and Faraday was not a calculus wizard by any stretch of the imagination. Now remember, the magnetic flux is what cuts the circuit through the area of the circuit C, and that in general is B dot dA. But really, we don't have to use all that mathematical formalism. We can think of it the way Faraday does, is that this is just the number of lines, magnetic field lines, that cut through that surface enclosed by the circuit. And how, if that's changing, then it induces a current, induces an EMF, and it induces a current. So the general situation is here. where we have maybe an arbitrary shaped circuit, and we've got a non-uniform magnetic field, and one would have to do this two-dimensional surface integral. But in all the cases we'll consider, we'll try to simplify things enough so that we can calculate the total magnetic flux in the following way. It's just B dot A. This formula will be plenty good enough. It assumes that the magnetic field is uniform, so it's all straight line, it's always in the same direction. Now it could vary with time, but only in its magnitude. And then the area of the loop, it's a planar loop. And I know then for uniform fields and planar areas that the B dot dA I can write as just the magnitude of B, the magnitude of A times the cosine of the angle between the two. The only addition that Faraday found was that if he took, he could increase the effect by wrapping this around many, many loops. So he could, in general, have n turns, and he rapidly started doing this with a fair number of turns in it. And I would call that probably the total magnetic flux. The B dot A here is the magnetic flux through one turn, and if there's n turns, you just multiply the amount of field lines that cut one turn times n. So it's sort of a magnifying factor. Well, that's the form that we'll generally look at, or we'll apply the flux formula. Again, the way to think about it is that it counts the number of magnetic field lines that cut through that surface enclosed by the circuit. The direction is given by something that we nowadays call Lenz's law. Lenz was a contemporary German physicist that had a nice formulation. I don't think Faraday knew this and used it, but I don't think he ever expressed it in quite as succinct a form and as conceptually well designed as Lenz did, and so that's the reason it's called Lenz's law. And Lenz's law gives us the direction of the induced current, or the induced EMF. So just to state it, the direction of the induced EMF and the induced current is such as to oppose the change in the magnetic flux through the area enclosed by the circuit. It basically states that nature is, for some reason, does not like to change. Whatever it's doing, it likes to continue doing. And so if there's a certain number of field lines that cut through the area enclosed of the circuit, it likes to keep that as close as possible to what it is. And so any attempt to change the number of field lines cutting through its area, it opposes. And the way it does that is by creating this induced current. And if there's a current flow, then it takes EMF to create a current. And so the EMF that produced that is the induced EMF. Well, all of these can be combined in the following form, and often are nowadays. That the induced EMF, that's just usually E, is minus the number of turns, ddt, the magnetic flux through one turn. And again, phi b, it just counts the number of field lines cutting through it. But mathematically, it's this. The negative sign is to oppose the change, to remind you that we're opposing the change. Well, with those two expressions, we can turn to look at some of Faraday's experiments and how he explained them. So these are sort of qualitative examples. Again, here's our coil. There's that ring, if you will, that's got a current detection device in it. And the original experiments take a magnet, north end, this end. Remember, magnets have magnetic field lines that emanate from north end and come into south ends. And if I'm moving that into the ring down the center, you'll notice that I've got some field lines from this magnet that cut through the area enclosed by this loop, which is perpendicular to the page. But some of them, this one right here, for instance, and this one over here, they're just outside. So this has three, and the picture has three magnetic field lines cutting that loop. But as I move this in, I'm gradually pulling more and pushing more and more field lines inside the area. In particular, if this has come in far enough, it's still moving. This field line here that was outside now falls so that it's cutting through the loop. And likewise, this one down here, if it's pushed through, it's going through the loop in this direction. So the number of magnetic field lines cutting through this surface enclosed by the circuit is increasing toward the right. I'm getting more and more field lines coming in. But nature is such that it likes to stay pretty much the same. And so it's going to induce a current, in this case going inward on the top portion. Remember, any current produces a magnetic field. So this induced current will in turn induce a magnetic field. And the direction, if you grab that with your thumb pointing in the direction of the current flow, it's going to swirl about this in this fashion. And that's going to create a magnetic field line in the opposite direction. In effect, sort of trying to cancel out this one that got pushed in as it was moving in, so that it maintains just three. Likewise over here, on this side, the current coming out at you, it induces a magnetic field swirling about it this way, and so on the interior it's coming in this direction, and that tends to cancel out this field line that got shoved in. So that's a use of Lenz's law to find the direction of these rings, or the current through the rings. Now if you come back up to the original statement of this and apply these to this, you should be able to verify that Lenz's law will give these what was observed by Faraday. He did it the other way around. He observed these and got at his statement of what we now call Lenz's law. You can look at the south end, pulling it out. So if it starts off close and it's moving in this direction, well, it's a strong field here, so there's lots of field lines that are cutting through it. But as it pulls it away, the field's getting weaker and weaker. And so this line that was inside and here now no longer is inside. Nature starts off like this, and it wants to stay pretty much the same. And so it induces a field, in this case, in the same direction. The induced current is going in the top. That produces a field going this direction. And so that tends to replace this one that got pulled out. It adds one due to the induced current on either side to replace those, to keep the number of field lines as close to being the same as possible. All for the switch opening and closing. You can do similar things. If the switch is closed, we have a current flow. It starts off with nothing, and then I close the switch, so the current starts to flow in this primary coil in this direction. So it creates a magnetic field due to the current flow in the primary. Well, it originally had no field lines cutting it. It likes to stay that way. And so once this current starts to flow, the field comes up and cuts through the loop in this fashion, and it induces the current in the opposite direction to try to cancel that field line that was created during the time this field is changing and building up there. On the other hand, if the current's been going for a long time, here, and one then opens the switch, so open the switch, then this current drops down to 0. But by this time, the number of field lines cutting the secondary coil over here is these two, and when there's nothing, they're going to go away, and so the induced current will be such to try to replace those. This one disappeared, and so it tries to induce a current to make it so that that the current or the total number of field lines stays the same. Well, that is sort of a qualitative description. Lenz's law is used to get those directions, and then the full statement I usually use in this form, but sometimes I use it the other form. Like so. To quantify things, we'll need to start looking at these in one form or another. But we'll do that through some typical examples.